Hi everyone. It's 9 o'clock on the dot. I think we can then start the session.
Yeah,
Welcome to our session of machine learning as well as artificial intelligence. Today we are graced with Dr. Professor Najam Hassan as well as Professor Ping Jia. Right. So yeah, I think please do guys enjoy the session. Please note that the session is recorded as well as live streamed to YouTube. Should you need any of the recordings. Thank you. Over to you, Prof.
yeah. Hello. I hope you can hear me.
Yes, you're audible, Prof.
Yeah. Okay, so welcome for this session. I'm Najam Hassan, and I'll be touching about the initial, a short introduction to machine learning, and I'll share the Jupyter notebook which we shall be using. In fact, I can share with you, share it with you right now, so that those who are interested can run as we proceed. Uh, Just a minute, I'll first share the, I'll be sharing two files. Okay. So, what is machine learning and why, what we are going to do? This is the basic outline of a short presentation I'll make, which will discuss what machine learning is, what are the different types of learning, what is the different data presentations we have, the type of data we have in astronomy. And we'll look at clustering methods, dimension reduction methods, a little bit of regression, and some examples from astronomy. So, what is machine learning? Basically, we are living in the age of big data. There's tremendous amount of data flowing now, even in astronomy. There's terabytes, petabytes, exabytes of data which is coming in from various astronomical surveys, and the speeds which we require to analyze this are going up. The computers are becoming very powerful and fast. We have gigahertz, teraflops, and high uh, speed data networks. And new algorithms have to be made to analyze this complex data. All these three aspects help create the current boom in machine learning. So, as Arthur Samuel defines, machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. Right? Earlier, we had set of data and we had programs, and we told them how to access this data, how to analyze, specifically specified it. But now in machine learning, we don't have to program each and everything. We train the machines to handle data and to make inferences. See, for example, we can train the machine into learning from images what is a spiral galaxy. We can give different spiral galaxy images, and this is the training set. Or similarly, we can give them a series of different elliptical galaxies, and we train the machines. And then from a survey where you have a lot of data collected from surveys, the machine can identify which galaxy it is, whether it is a spiral, lenticular, or an elliptical, and it can classify the galaxies in uh, different bins, distinguish ellipticals from spirals, spirals from lenticulars, or distinguish stars from galaxies, and so on, and do that. So machines are extremely powerful and very fast at doing so. So it reduces the effort of human experts who could otherwise, who earlier had to see these galaxies and bin them. So the basic idea is you have the inputs, you have these x1, x2, xi, and we have certain y outs. Yeah, so you have this data. The basic idea is to find a function which predicts, a function which defines looking at your data and classifies it into, for example, in the case of say galaxies, it looks at various aspects of the image, and the function decides and uh, defines a function which will predict what uh, certain images. So when you feed in a specific uh, value, then it predicts. And then you look at the errors if it makes, and from error, you keep refining this predictor functions. Finally, you reach a point where your errors become the least and so on. So there are different types of learning. We have supervised learning and unsupervised learning. In supervised learning, we use labeled data, and you have the input and the output pairs to train the machine to do that. And then it tries to calculate from the surveys what it's actually doing. While in unsupervised, we use unlabeled data, and the machine itself finds the hidden structures from it and finds them. So the supervised learning is usually used in classification and regression, while the unsupervised one is used for clustering and dimension reduction. So as we proceed, these things will become more and more clear. So for example, in supervised learning, we have, say, these Indo-Arabic numerals. We train the machine with 0, 1, 2, 3, 4, all these 9, and we are Roman numerals. And then you try to give numbers and you make the machine predict. So for example, your guess in the first case is Indo-Arabic. The label also is Indo-Arabic, so it's fine. The second one, the label says it's a Roman number and your guess is also Roman, so it's going fine. But in third case again it goes fine. In the fourth case, it is the label says it's Roman, but our guess suppose was wrong, and we say it's Indo-Arabic, and we are going wrong. And the last one again is fine. So the accuracy, you look at the accuracy of that. So out of five, four of them were right. So the accuracy of this is about 80%. So we also have reinforcement learning, where the machine keeps correcting itself and reinforces its knowledge from the data, and then it analyzes, looks at the predictions, and it learns the by mistakes it makes. It's something which even humans do. When a child is initially told what is a chair and what is a table, the child may show a stool and say, "This is a table," and you would say, "No, no, this is not a chair." So you keep correcting yourself again and again, and finally you get the right picture of what a stool is, what is a table, and what is a chair, right? So the algorithm explores the data, it learns by trial and error. For example, in astronomy, you have a robotic telescope which chooses a star or a galaxy to observe next. And it makes this from iteratively by uh, either it can use signal to noise ratio to keep correcting what it has to hunt out and look, or you can, on the basis of the observing time or the scientific priority. So you have this range of learning, which is good. So types of data and representations, you could have categorical data. For example, in galaxies, you have elliptical, spirals, irregulars, right? Like you can have normal ones, you have males and females, or good students, bad students, and average students, right? So you have categorical types. The mutual labels are mutually exclusive, and they're encoded as numbers. but arithmetic is not meaningful here. You give labels to this ellipticals as zeros, spirals as one, irregulars as two, and so on. Or you could have ordinal uh, data where, say, for example, the seeing quality is poor, fair, good, or excellent. And we have ordered categories, and you have comparisons that are meaningful in this. Or you could have numeric data where you have integer values or floating point numbers, a real number, to indicate red shifts or uh, RA and declination. It could be for fluxes, magnitudes, wavelengths, and so on. So you have basically mathematical data. And you can do mathematical operations which are meaningful here, adding, multiplying, dividing, and so on. The values are often normalized before machine learning mm, algorithms are applied to it. We'll see examples and see what I mean by this. So this is an example where you have elliptical spirals, irregular, or a star, and we give labels to it, and we encode it by these strings, these labels. Okay. Similarly, we can have stellar spectra. Stellar spectra is a signal measured across wavelength, and the derived representation is the flux sampled at regular wavelengths intervals. And the printed representations are, we have spectral features, we have line strengths, we have continuum shapes, and we use Fourier or PCA coefficients to look at it. So in summary, we define the task, we get the data, we choose the right representation, we explore the data using statistically and visualization techniques, we prepare the data, we select a model, we train and evaluate, and you evaluate on a test set, and then we launch the whole algorithm and do our work. So, so reproducibility in machine learning, we have computational reproducibility, meaning obtaining consistent results using the same input data, models and analysis conditions. We have sources of stochasticity, random initialization, shuffled data sets, changes in software framework, and noisy model components. The tools which we use are version controls, dataset variation machines, saved hyperparameters, and model sharing and experimental tracking. We use techniques of clustering, where you break up the data into different clusters. We will be doing examples of this. We choose a number of clusters which we want. We place centroids to it and assign each point to the nearest centroid. And then we move the centroid to the mean of this position and repeat this position till the time we break the whole data into the certain groups and centers. Okay, so as we come further with the examples, it will become clear. And dimensional reduction. Usually we have astronomical data which have many parameters. And when we are we are trying to study a certain aspect to it, it's important for us to find out which are the most important parameters which are used to understanding the phenomena behind. And so you reduce the dimensions by using the principal component analysis method, right? We look at this as if further. So, for example, if you want to divide the whole data and you want to find out two principal components, we uh, see the two principal components and see where the variation is minimum or maximum, and we see which are the components which are the most important aspects of that. So as we proceed, we will see how PC is used in stellar spectra. I will show you, demonstrate this with actual data which we have. And the failure of PCA comes when the data lies on a curved or a regular or a circular thing, where your theta, the angle, the azimuthal angle, and R. They don't make much of a difference, and this is where it could fail. So in summary, machine learning learns patterns from data. Supervised learning uses label data. Unsupervised learning finds structures without labels. Data representation is central to the performance. And k-means group similar objects into k-specified groups. PCA reduces high multidimensional data such as stellar spectra, and astronomy provides rich data sets for modern machine learning methods. Right. So with this, we come to the end of the presentation, and I will go into I'll go into basically. Can you see my screen?
Yes, we can.
Yeah. So machine learning in astronomy,
Sir, we are
astrophysics.
seeing your earlier screen only. Thank you.
You, you,
We are not
you
seeing
can't
from
you
Zoom.
can't see
Yeah.
the Jupyter notebook.
No, sir,
Sorry,
no.
what
No,
we
sir.
can see is just a screen. I see you
Okay.
share YouTube video, right?
He's showing the
No,
slide. Yeah.
Just a
this,
PowerPoint.
I think
Yeah.
this is fine.
Okay,
Now
okay.
you
It's okay.
can.
Yeah, it's
Yeah.
okay.
Yes, sir, now it is visible. Thank you.
Okay. Yeah. So we'll get back to this in a more organized way. So machine learning for astronomical data analysis. So this Jupyter notebook is a very short introduction. And basically, to iterate, as astronomy enters the era of big data, with large surveys like Zwicky Transient Facility or Vera Rubin Observatory Legacy Survey of Space and Time, we have tremendous amount of data, and hence machine learning has become a very essential thing to analyze this data. So at its core, machine learning is a science of teaching computers to learn patterns and to make decisions from data without being explicitly programming it, right, for every specific task. And like I said, you have supervised and unsupervised type of learning. And supervised learning, it's used for classification and regression. Goal is to predict a discrete category. The output is a class label. The basic question could be, what kind of an object is this? Is this an elliptical, a spiral, or a lenticular galaxy, or an irregular one? And the machine learning helps us decide, bins them into a galaxy, quasar, supernova, or and so on. In regression, the goal is to predict a continuous numeric value. So what is the numeric value of this property? And for example, what is the galaxy's redshift? What is the star's temperature, and so on? So when you have specific numerical values, you use the regression to do that. In unsupervised, there are no labels. It's the analogy is you give a child a box of mixed Lego bricks and ask them to sort them into different piles without any prior instruction. They might group the bricks by color, by shape, or by the size, and the algorithm discovers the structure of its own. Pushing this analogy to an astronomical example, we have a survey of galaxies of all morphological types, and you want to sort them into different bins without any prior instructions. We don't train the machine into doing that. We just give the survey, and the machine decides without any prior discussion. It can decide to see the patterns. It can classify galaxies by color, by shape, by chemical enrichment, or by the size. So the algorithm itself discovers, it sifts through this large amounts of data and discovers the structure of its own. And in unsupervised used in learning is often used for in clustering. So the general question is, are there natural groups in my data? And we find groups of stars with similar proper motions in the Gaia data sets, or groups of galaxies based on the observational properties, right? Or the other thing is dimensional reduction. The goal is simply to of a data set by reducing the number of input features while retaining the most important information. So the question is, can I simplify my data without losing key information? For example, you take 100 different measurements of galaxies and find the three most important underlying variables that describe most of the variations in data, right? So it can be used in anomaly detection. The goal is to identify data points that are significantly different from the rest of the data. Okay, so it scans the millions of starlight curves and flags the ones which show variability patterns which have never been seen before. So you can pick up anomalies and you can find interesting objects and so on. So here's a table which gives you the machine learning task, classification, regression, clustering, anomaly. These are just the four ones which I am showing. Apart from that, there are many more, but these are the common ones. And the time limitation will not allow us to get into more than these tasks. So classification can be used for object identification, say in images, supernova typing from light curves, galaxy morphology classifications, right? And regression, you have photometric redshifts, you have stellar parameter estimations from spectra, and so on. And in clustering, we identify star clusters and associations in large surveys like in Gaia, discover galaxy groups based on shared properties, and anomaly detection, searching for novel transient in real time data streams from Zwicky transient and LSSD. So in summary, we have this machine learning analysis supervised, yeah, and let's not get into this. I'll I will now open a specific. Where's my? Oh, just a minute. It's right here. Okay. So here we are looking at machine learning for which is very specific cases of with astronomy data. With in this notebook, we'll be generating synthetic data because that will be simpler one with it for faster computations and so on. And then you can try this on actual archival data which you can download and do. So important libraries which we have to import. Now you are very familiar with Jupyter notebooks and Python programming. So we import NumPy, we import Pandas as PD, we import matplotlib .pyplot as PLT for plotting, and we are using the Learn Skykit Learn model selection, import train test split, and from scikit-learn pre-processing. We'll discuss this as we proceed ahead. And these are the ones which we have to import. And we are using Seaborn. We are using a certain style sheet just for the beautiful graphs which we get. Okay. So what we are doing it is we are importing this train test split, as you have noticed here, train test split from Skylearn model selection, because the basic idea is because it handles common machine learning preparation steps. It is used to split the data sets into training and testing parts. In this notebook, the model learns from the training data, and this helps check whether the model can make good predictions on the new unseen data instead of only memorizing the original data sets. We imported standard scalar from Skylearn.preprocessing. It's basically to standardize the numerical features so they have similar scales. See, for example, if you have one column which has values, say 0 0.5, 0 0.3, 0 0.2, and so on, while some other column has 20, 30, 100, then certain algorithms, for especially the principal component analysis and the regression ones, they get confused, because you have one parameter in decimal points and the other one is in uh, tens or hundreds. So you standardize this. This standard scalar is used to normalize the data. Okay. So when you do the standard scalar transformation, usually it roughly re uh, uh, scales the data with mean 0 and standard deviation 1, right? Roughly it gets into that. Okay. So now we are creating an astronomy photometric data set. We are simulating uh, a data set similar to SDSS, Sloan Digital Sky Survey, and we are creating where we have stars, galaxies, and quasars, right? So I'm creating 1,500 such objects, and randomly, yeah, we have seen this in NumPy, this random one. So we are randomly creating stars, galaxies, and quasars. And the n size is defined here 1,500. And the p-values are zero point 0.4, zero point 0.4, and zero point 0.2. And I have created a, a data set, right, where we have U, G, R, I, and Z. These are the different colors with different redshifts. And we have classifications which are star, quasar, galaxy, or a star. And U underscore G, these are these magnitude in U, magnitude in G, the subtracted value, U minus G, G minus R minus G, the colors in R minus G, right? And now astronomers often use the colored indices such as U minus G, G minus R, and these magnitude differences are the different magnitudes you measure in different filters. And we are plotting them. And this is a color-colored diagram, U minus G against G minus R. And when we are plotting them, we are seeing that the galaxies are appearing in one part, while the quasars, the orange ones, are having a different color, and the stars are falling somewhere, right? So this is a visual one. Okay, so this is just showing the data which we have constructed, and in the color diagram, they are falling in different regions. Okay. So we train in this section, we see how we are training. Yeah, we are going for the supervised classification system. We train the classifiers to predict whether an object is a star, a galaxy, or a quasar. Okay. So this is the set which we have generated, from which we have 1,500 objects, and we are using this to do that. Okay. So by running this feature equal to U, G, R, I, and so on, what we are doing is we are creating a list and we are storing it as features. And X we are defining these features, and Y as the classes, right? We have. Okay. So basically the explanation for what I have done. So the code trains and evaluates the machine learning models that predicts whether the object is a star, galaxy, or a quasar. And this statement features creates a list of input columns. These are the features that the model will use to make predictions. These U, G, R, I, and Z are the brightness or the magnitude values in different filters. And U underscore G, G underscore R, and so on are the color indices, meaning the difference between the magnitudes. These help describe the object's color, right? And the color gives us the temperature or the spectral type of a object. X, this selects those featured columns from the data frame DF. And so the X contains the input data, and the Y selects the target output columns, right? So we are basically looking at these. Okay. Then the important one is this line where you have X test, Y train, Y test, and train test split. So basically, what we are doing is we are splitting this the 0.25, and you have this random state X, and right. So basically, what this means is this splits the data into training and testing sets. X train and Y train. These are used to train the models. And X test and Y test are to test the models. And the test size which we have specified is 0.25. That means we are saying 25% of the data is kept for testing and 75% is used for training, right? So what we do is you have a set which is labeled data, which we know what it is. And from 75% of this is used for training it. Uh, and 25% is to test it. So then you run it on the whole thing and you try to recover and see how good your training set was. Okay. And this random state 42, this random number 42 which we put, it is for a reproducibility. When you keep using the same number 42, you will get the same results each time you run the code, right? When you want to change the code, you will get different random. And stratify here is Y, where Y we have defined it as class. Class, if you see, are stars, galaxies, or quasars. Okay. So, and then when you run it, you find out what is the prediction, recall, and the F score, which gives you the balance between the precision and the recall, and how many test samples belong to each class. So when we have run this thing, we get a summary of the whole thing, if you see here. And the accuracy it shows is 0.98. And the precision for galaxy is 1, right? 100%. For quasars, it's 0.99. And for stars, it is 0.97. Okay. And right, so this tells you the F score and the support and so on. Okay. So basically, so important is in now we are doing the random forest estimation. So uh, from the CLS series features importance, we index some features and we sort by value. And we are looking at that when we are looking this U minus G magnitude was the most important feature in classification of these three objects, right? So the most important feature was U minus G. Next was its magnitude in U band. The third one was green minus red. Then the redshift was the fourth one, and so on. The least important was I minus Z. Right. So this is a thing which will show you which are the features which are most important in classifying galaxies from quasars and and stars from this data which we have, right? So the most important feature, according to analysis, is U minus G, and the next most important is the U, magnitude in U man. So coming to regression, we are not, so in the earlier one, we classified them and now we do some regression analysis. And this is the regression line it fits, and it's plotting and showing the data, the true redshift and the predicted redshift, right? So, uh, okay, so what we are looking at is we are defining galaxies from this DF galaxy, the data frame which we have class where the galaxies were there, and we are making it a copy of it and putting it into galaxies. And from X, the data set X which we are creating are the galaxies features and the galaxies redshift we have here. And then we are training again with the test size as 0.25, 25% we are keeping it for testing, and 75% is being used to train the data, right? And again, this random 42, this is being used basically for repeatability of the thing. So when you keep doing it. And regression, random forest regression estimator, we are using this to run it. And this command is used to fit this over the training sets. And okay, so to understand this code, this is the one. So unlike the earlier classifiers which predicted galaxies like stars, galaxies and quasars, this model predicts a numerical value and in this present example, we are using the numerical value of a redshift, right? So a reg equal to random forest regressor, n estimated 200 random state 42. This creates a random forest regression model. A random forest regressor is made up of many decision trees. Each tree predicts a number, and the forest combines the predictions, usually by averaging over them, right? And the estimator which we are using, 200, means we are using 200 decision trees uh, for that. And this random state 42 makes the result reproducible so that the model behaves the same way each time you run this notebook. And this reg fit, we are running it over the trained data set which we have, x underscore train, y underscore train. 75% of this is used for the training. And this trains the regressive models, right? So X-train contains input features such as brightness values and color indices, and Y train contains the corrected numerical values, and models learn from the predictions, such as the galaxy redshifts, right? And when we run this Z prediction reg.predict, so from this test data, it's predicting what are the values, and this uses the trained models to predict the value of the test data, and the zpred stores the predicted uh, redshift values. Here Z represents the redshift, right? And this root mean square error gives you the error in the prediction, right? And it's very important to see what the value of this RMS is. Like, for example, in the above case, which when we ran it, we got the root mean square value as this 0.29543. Yeah. So now it's important for us to understand what this value means, and getting a value of 0.295, whether it is a good or not. So basically, um, uh, uh, you have to realize that this RMS value can range from 0 to infinity, and 0, this RMS value can never be negative. RMS 0 means it's a perfect prediction, right? And very often when you are handling with data, you will not get a 0 prediction, because there are various errors which creep in, observational errors and instrumental errors, and right. So you will never get 100% one, but yeah, if you get 0, it indicates prediction is perfect. A larger RSM means it's a bad prediction. And it's important, you have to realize that it's very important to normalize your values to check what these RMS values are. Okay. So in our case, how do we do that? I am taking the Y minimum and Y maximum. Yeah. This is basically so I'm just writing down what is the Y minimum value which you have and what is the Y maximum that you have. And if you subtract the two, you get the range of Y. So your root mean RMS divided by the range over which it is done is important to do it, right? So I am getting this RMS value and this, and I'm seeing that it is 0.2061, right? So this means that the error is about 20% of the full range. The whole range of Y, redshifts range from the minimum of 0.026 to 1.458, right? So you have to see how the Y is at over what is the minimum value, maximum value. And in that context, you have to see what it means. So what we are seeing is there 20% of it. But also, you can find out the mean redshift value, and you can also estimate that the error is about, yeah, so but when you run it over the mean, you run it over the mean value, which is 0.295, you get it's about 70%. So the mean over the mean, it is 70%. It means 70% of the data is good, right? So I would say that this is not a very good prediction rate. What it means to say is this. It's not very small, but it would call it moderate to a fairly large value. So the prediction is not extremely big, right? So 20% or 30%, right? When you're comparing it with mean, you are getting about 30% of error in that. Okay. Yeah. So it's always good. So, and here we are again seeing how you have to rescale the values to do that. Okay. So unsupervised learning, where we use the k-means clustering. So again, we are using the same database which we have created, and we are running this in an unsupervised way. We are using the k-means. Right. So look at this part. The scalars, we are using this to rescale the features. Okay. Okay. So you transform the data into rescale values, because if certain uh, column values have, for example, you see here, the data which we have, uh, you have 16, 20, 21, so on, but uh, in some places the values are going from 0.29, 0.23 point. Okay. So when you are comparing 0.2, 0.3 with 16, 20 and all, you get errors in that. So you have to rescale those values when you are running this. So the code performs k-mean clustering on the astronomy color features. The scalar, yes, the x scaled, we are defining another one scale. This standardizes the selected features so they have similar scales. And this is important because k-means uses distances, and the large scale features could otherwise dominate the results. Okay. So it's very important to rescale it. For example, instead of using your u minus g is in decimal points, while the parallax is in tens and 20s. So it will start dominating, it will start showing that parallax is playing a bigger role in clustering, right? So you have to rescale them. This def num underscore k-means, this defines the simple k-means function using numpy. And this numpy random dot default, this creates a random number generator with fixed seeds so that the results are repeatable, like we have discussed earlier. The center x reg dot choice, this randomly chooses initial cluster centers from the data. So you have the data distributed in the field and it randomly chooses some data centers. So it defines data centers, it calculates distances of each point from these data centers, finds the mean of it, and then uses that as a data, right? So it recurrently goes and then it groups into data. So it randomly chooses the initial data centers from this data. It calculates the distance from every data point to this cluster center. Then it labels uh, those points, assigns each data point to the nearest cluster. Then the next new centers, it again recalculates each cluster center as the average of these points and assigns to the cluster. And this command, if np all closure, if the this is to stop the calculations if the distance between the centers and the new centers is not much new, right? So it's recalculating new centers repeatedly. And if you want to break out of the loop, you define a size. If the difference is there's not much of a change with the new centers, then the algorithm, the process stops and it returns the cluster number for each object. And df cluster numpy x means runs the clustering and stores each object assigned cluster into a new data frame called the cluster. In short, it groups the astronomical groups into three clusters based on their color features without using the known class labels, right? So we have seen how, yeah, this is the other classification which it has done on the basis of yeah, so this is the clustering one. And you'd see that what you got in the supervised and unsupervised are pretty much accurate, right? So in the U minus G space where we use the supervised, we used we first gave labels to these objects, trained it, and they ran it on the whole field. Or when we didn't use the labels, but we use regression models to do that, you see that the regression models are giving you pretty much the same kind of a thing, right? So this is two different ways of classifying data from, right? So we are getting the zero class galaxies 520, 541 quasars, this thing. Okay, so now coming to the synthetic stellar spectra. Yeah, so we'll construct some synthetic stellar spectra, hot stars, sun-like stars, and cool stars. And then we'll try to do some kind of analysis using that. So this is the block which builds this one. NumPy.linspace 380 to 800, 300 data points in wavelengths. Yeah. And we are making spectrum of different type, hot type, sunlight type, and continuum one. These are, right? So I'm running it and I'm plotting it to see what it is. And this is a demonstration to show how principal component and analysis is used for dimensional reduction of stellar spectra. So we have 300 wavelength bins, right? Why? Because we have used NP lens space from 380 to 800 and 300, and we are putting it into three bins: hot, sunlight, uh, and cold ones. And so what I have given you are the actual, yes, the ones which we are plotting here are synthetic wavelength. Is but the actual one looks something like that. So this is for the sun. This is the sun spectra, and these are the different spectra for hot stars and sun-like stars and cold stars. So this is what the actual spectra looks like. But what we are dealing with in this notebook are synthetic ones. Okay. So now we are running the principal component analysis. So basically, we want to find out they have in the uh, table which we have various parameters, right? There are many parameters, but from which we want to pick up what are the parameters which are most important in deciding um, the large spectra. Okay. So, and it is, you see that the variance is given you, total explained variance is here, and it has broken them up into different PCS. The cool stars are sitting here, or the hot stars are sitting here, and the sun like stars are sitting here. So you have PCA1 and PCA2. So it has found out the two principal components, 1 and 2, in which you can break up the different objects very beautifully, right? So explaining that the code, the scalar and the scalar scale, these are to rescale the data because this is to standardize the spectra of each wavelength to the similar scale. That matters because PCA is affected by feature size. Without scaling, wavelength and large numeric values, it could start dominating the results. This PCA n component equal to 2, which we have used here. We are saying we want to find out two principal components. You can use it with 2, 3, or whatever. So in this case, we are trying to find out basically two principal components of the data. So we are specifying a component equal to 2. This creates a PCA model that will reduce the data to two principal components. That is, reduces many spectral measurements into just two main features. And the principal components are new features that summarize the most important patterns in the original spectra. The spectra dot fit transform, right? So we are running it on the scaled one, the scaled spectra, and this fits the principal component analysis to the scale spectra and transforms the original data into a two-dimensional PCA coordinates. So instead of representing each spectrum using many wavelengths values, each spectrum is now represented using only two values, PCA1 and PCA2. And this explained, this statement is just to print out the explained variance ratio. This prints and shows the original variation captured by each principal component, which is 0.65 and 0.2, which means the principal component 1 explains 65% of the variation is given by principal component 1, and the variation, the principal component 2 explain only the 20% of the variation of the data, right? So PCA1 is the more important one. And if you want to find out the total, what PC1 and 2 indicate, if you look at the combined variance ratio, so 85% it is giving us a value of 0.85. This means that the two-dimensional PCA reference keeps 85% of important data variation in the original spectra, right? So when you have many parameters, we can break down into the principal components and study those, right? So interpreting it, um, uh, which shows the the PCA1 is given in blue, and principle to use that, and which gives you the basic ways. Okay. So with this, I will come to an end, and if there are questions, you can ask on chat or so. And I'll just see if there are 3 more minutes before Peng takes over. If I'll see if there are any questions which I can answer now. And I've shared
Sir,
this
I
in the
have
group.
one question if I can
Yes.
ask. So, in image analysis, suppose we have a image, data image where there are many different objects. So, if we want to do image analysis, do we need to cut the regions and for a particular image and provide us data, or we provide the entire image?
Can
How
you?
we go about it?
No. So see, I've demonstrated that you are talking about which PCA one, or you're talking about principal component
Like
analysis?
in images, like suppose we are classifying the galaxies, right?
Okay. Yeah. Yeah.
Spiral. So there
Correct.
we have a whole image where there are so many types of objects, except for
Correct.
those also. So how we, uh, clean the data for our
Yeah.
analysis.
Yeah. So there are two ways you have. One is the supervised, and the other one is unsupervised. In the supervised one, you first train the algorithm by you keep showing the images of spiral galaxies, and you say that all these images are spirals, right? So you say hundreds and thousands of images of spiral galaxies taken from different angles, different viewpoints, and so on, and say any image which looks like this is a spiral. Then you show images of ellipticals, many images of that, and you train the algorithm to understand that these images are all elliptical galaxies, and similarly lenticulars and so on. Okay. So you have these training sets with which you train the algorithm, and the tables which you create, in that you have the labels. You have these tables of galaxy names, their position, velocities, and you are in the table itself says this is a spiral, lenticular, and so on. And from this, this is the training set, And then when you give the survey data of all other galaxies, millions of other galaxies, it looks into the features and it picks up. So the test data which you have will not have those components. It won't say it's a spiral or lenticular, but it compares the images, and by the features it tries to, it traces whether it's a spiral or not and bins them out. Okay, so that is the way how uh, uh, you use the supervised learning method. And in the unsupervised ones, you train it without the labels, and the set itself tries to seize features and tries to binge them into different groups, and it tries to binge them as spirals, lenticulars, and so on. And then you verify it and say whether the accuracy is good. If the accuracy is good, then you run it on the data where you have not, it has not been classified, and that sips out, it pulls out the spirals separately, lenticulars separately, and so on, right? So, yeah. So, and in when you are training and retrieving, you first do it on the training set which you know very well, and you give only 75 of the data to check it. Then you run it on the whole thing and you see how accurate it is, because the data set is known to us and it shows that how well it has found out what is the accuracy limit. If the accuracy is good, then you run it on the other data. Okay. So,
Sir, I was saying like if we have one image where there are multiple objects, then
no,
do we
no.
need to divide it into separate small images and then give it as data, or how to go
Um,
about it? I was
Yeah.
just confused.
So when you are training it, you have to give multiple images to train the data set, because you can't train it on the basis of one image and do it. You have to show. And okay, so when you are training, you have to suppose you have a galaxy and you want to know whether it is a spiral or not. So you train it by showing many spiral galaxies, and then you give this image, and it matches with all the galaxies which you have said which are spirals. And if it matches perfectly, then it says it's spiral, or it says it is not. Okay, okay. You get my point.
So
So
yeah,
your
I
single
got it.
galaxy, yeah, yeah.
Yeah.
So first you train with many images and say this is what a elliptical galaxy looks like, because elliptical galaxies can vary in size, in shape, in inclination angle, and so on. So you have to show, because the elliptical galaxy which you are going to show, or a galaxy image which you don't know whether it's elliptical or spiral, it can be inclined at any angle, it can be, right? So you have to show many ellipticals in different inclination angles and sizes and so on. And you compare yours with that, and compares and says if it matches all of them or some of them well, then it says it's elliptical. If not, it says it's not. Okay, so I'll stop with now this, because Peng will do the second aspect of it. Thank you. Over to you, Peng.
Okay, thank you, Professor. And now it's my time to share with all things. Let me just share the screen. Okay, can you hear me? Okay,
We
Yes,
can.
sir.
Yes, we can hear you.
good, good. Okay.
Yes, we can hear you.
Thank you for the presentation made by a professor in the last hour. And now I will share some of the application with machine learning in astronomy. And I use all these I Python notebook files from the GitHub, and I will share it in the case. Let me share. Sorry. I will share it through the team. Okay, uh, just to stop. Now I share it with. Okay, I have sent all these files uh, to the discussion panel, and I suggest to everyone that we can actually use a Google Colab to do our exercises, which would help us to finish all these things like environment or something like that. I will continue with the machine learning part, which is just discussed by Professor recently. The first thing I want to talk about is about the regression and how we can do regression with machine learning. For example, uh, f- for the start, I want to say that all the machine learning problems, like we have discussed earlier, is to model how people to deal with all this data. And I want to say that if we use a machine learning or similar algorithm in the future to to solve astronomy problems, we need to first think about how humans can solve this problem, and then we can select some algorithm, and we can actually use this algorithm to solve our problem. The first thing that I want to share is actually the regression. The regression is actually do things like, oh, sorry, is actually do things like we do the calculation to estimate a value that reflects what we want to know. And the regression in this talk is about the how to calculate the redshift of galaxies with photometry data. And we all know that if we want to do the redshift estimation from spectrum is actually carried out by we select them, we see the peak of the spectrum, and we calculate the distance between these peaks in the we see the observed wavelengths. We can calculate the redshift. It is a basic idea of calculation of the redshift. Okay, it is what human beings do. For example, if we just see the spectrum and we estimate the distance between these peaks, and we can calculate out actually the redshift here. Okay, and now we select the algorithm, and the algorithm is like what I have discussed earlier, and also the professor has presented in the last presentation. Is you pick up something that can do the regression. Okay, uh, there are many algorithms that can do regression, and now we in this part we actually will show some of this algorithm. Okay, and we just ignore all these astronomy part. Okay, why we calculate regression? Sorry, why we calculate redshift with this spectrum is important for astronomy for astronomy study. We just give up to how we do this redshift estimation. Okay, and because in most observations what we can do is actually some photometry data. It is spectrum, okay, it's good. But actually what we can do is do the photometry data, which is actually integration of this spectrum. Like we show here is a SDSS uh, broadband observation, sorry, broadband emission file. And we can see that it's UGRIZ band, and we can see that if we bring this energy into this broadband, we can actually get some peaks. And we can find that if we find some galaxy that is blue and it becomes green or becomes red, we can actually say that there is some red shift between these galaxies. So it is a basic idea for redshift estimation. So if we do some photometry, we can actually use this multicolor photometry data to calculate the redshift. From this basic idea, we can actually select some algorithm, okay? Before we move on to the detailed algorithm, we need to do some data trim. For the data trim, it is important for machine learning algorithm because we know that machine learning algorithm, like we discussed in this lesson, we use the skit-learn, which is a highly competitive API. It means that you need to make your data that is suitable to be accepted by the algorithm defined in the scikit-learn. So we need to do this thing here, and we can see that we read the data from NPY file, which represent the with the photometry data and also the output data here. And now we load the data with numpy load, which load the data into our input path. And all this data, as I said earlier, we can get from the GitHub Okay, sorry, I do not upload the GitHub file. Okay, these are the data that we used in the, oh, let me see. Okay, it is data that we use in this lesson. It is the NPY file and a CSV file. Okay, let me share. Let me share the, let me also share the, okay, because of, I will shift it to the, the change the, sorry, just first of all, I will share the GitHub. Okay. It's a link. Oh, it is a link for all the files and also the. And now I will shift the color. Sorry, shift the color. Uh, I will shift. How to change it to. That is here. Let's shift it to. How about this page? You can you see this page? This things in the IPython notebook? Okay. Let's move on. As I said earlier, that we need to convert all this data that is readable by the functions defined by the scikit-learn. Okay, let me see. Oh, okay. No problem. Okay, we see that we read all these photometry data here from the data UGRZ, which is actually defined by the NPY file. We just ignore it because if you encounter some new observation data, there are some different definitions. And if you use some AI like ChatGPT or Gemini, it can help you to basically reload these data into your file. And then the second step is that we need to remove all these non-definitive values. Okay, for example, if there are some we see like the bad pixel or some things like that, there will be some infinite values. So we just remove them, and we set all these values within the valid SDS and magnitude. Okay, from the first step to the second step, we actually cut out the values that are not physically visible in our data. And in the third step is that we need to actually remove the unwanted spectrum class. Okay, there are some classes that define we do not want them. Okay, from all these three steps, we actually made the data that is readable by the scikit-learn algorithm. Okay, and then we combine all these masks, which actually masks all this data that we do not need or not useful in our application. Okay, if we do not do this step, actually the algorithm will fail in some cases. Okay, and then we use the pandas to load this data into the DF file. And now we can run this step, okay, to get the results here. There are some warnings, okay, which can just ignore these warnings. It's not important to do the things. And as I said earlier, that if we want to do the redshift, the estimation, we can actually use some color information, okay? And here now we can do the color transformation from to do the difference between the different photometry values to get the final results. After this step, we can actually get the UGI, the magnitude, and also the redshift, which is actually want to estimate, and the redshift error, which is actually the estimated error between the ground truth value and also from the photometry values, and also it including some noises during we do the photometry or redshift estimation, and it is what we get from the of the color difference between all these photometry results. And then the next step is that we just check what different spectral class we get here. Okay, as we can see the discussions earlier that some people ask whether we can use a very large with a very large data set to solve all the problem. Uh, it is actually not a good solution for real for real applications. For example, here we can see if we just check the spectrum class, there are some very high unbalance between the different spectrum. For the class type 4, there are only 34, and for the class 2, there are actually 11,000. Things like that. If we just increase the data set by some amount, for example, 10 times or 100 times, it will increase the number of the data set, but will not solve the unbalance problem. So if you train some neural network, or if you train something like a regression algorithm, the model will just focus on the specific class like this. Okay, it will partly pay attention to the class 3, but will just ignore the class 4. So sometimes we need to do the balance. We need to increase some real classes or some real type into our data set. Okay. After we get the data set, the next step is that we can actually draw a picture to show the uh, okay, we can actually draw a picture to show the photometry result and as well as the colors here. And uh, if we do some astronomy observation, it is just very obvious to say the magnitude distribution of of these galaxies, and also the color index of these galaxies and the redshift estimation. And we can see that all because of the observation ability of the SDSS limited, so we say the redshift is just around well, okay, it's below 0 point about 3 or 4. Okay, it is actually some very important ideas here. So if you design some regression algorithm to estimate the redshift from the things like SDSS, we know that the redshift that is larger than 0 0.4 actually is not possible because of the observation limit, and as well as the absolute magnitude of the galaxies. So it is important for the future applications. We can actually put our knowledge about the universe and also about the observations into the model when we design this model. So we can directly cut out all the estimation values that are larger than 0 0.5 for the redshift distribution with the SDSS data. Okay, now we have actually say what data looks like, and the next step is that we build some model to learn the relation between the photometry, sorry, the magnitude and also the redshift. This step is what we do here. This step does here is actually build the data set to train some we see some machine learning algorithm here. Okay, we see that we choose the features here, u minus g, g minus r minus I, and I minus z. So actually we can think here why we do not directly use the color like u, g, r, z as the features. Okay, why do not directly use it? Instead we use the u minus g, g minus I, r minus I minus z. Students, if you are interested in this problem, you can actually check this problem here. Okay, you can check if we directly use features like the magnitude in different broadband to estimate the redshift. What is the difference between the features we defined here and the features we mentioned previously? It is actually some important problem in machine learning area about 10 or 20 years ago. It's called feature engineering. We actually design some features that is more feasible for some problem. Okay, it is just some examples here. Okay, we directly use features like it. Okay, and we use the features and also the target here which is actually the redshift. Okay, and we pick out these data from the DF files we defined previously. If you forget what we defined in the DF files, we can just switch back to visualization of the data. We say we pick out the U minus G, G minus R minus I minus Z, and also the redshift here as the training data. Okay, and some students ask how we get the training data. And we start here. We train a neural net. Sorry, we train a regression algorithm that can be used to calculate or can estimate the redshift from the SDSS photometry data. So the training data actually we get here is some data we collected in the SDSS, we can get the magnitude in different broadband. And the redshift here is actually can be actually obtained by the spectrum. Okay, we get spectrum here, okay, to estimate the redshift and redshift error, and we get the photometry result for the magnitude in different broadband. It is how we get the label and also the data. Okay, it is a step and it is the philosophy how we solve this problem. And as I mentioned earlier, it is for the SDSS photometry distribution. So the problem he comes here. If we use some different observation like DISY, okay, if we use DISY data, can we also use the SDSS data set to do the redshift calculation? Okay, it is a problem left for every student. You just think if we train a regression algorithm here, we use SDSS data. Can we directly use it for the DISY? Okay, for DISY, also for the redshift estimation. Okay. Okay, the results, sorry, the answer here we see that if we build a model for SDSS, in most cases it can only be used for SDSS unless we encounter some sky survey problem that has similar noise level and similar observation properties like SDSS. Otherwise, we need to actually carefully check the model with some new data. Before we can use it. Okay. Now we build a data set here. We collect the features that we want to use, and we collect the labels. Actually, it's the regression values we want to know from the observation data. Okay. Next step is we split the data into the training and testing sets. Okay, here we just use some predefined method in the scikit-learn package, which is actually the train test split. If you open this function in scikit-learn, you can find that. Okay, you can actually see the source code here if you're interested in some thing that it is actually just some function that randomly distribute. Okay, I can shift it. It is just a function that actually it's a function that randomly split the data into different data set. Okay, just it is just what it is doing here, and we will I want to discuss it here very because of a very important problem. Okay, uh, in the machine learning algorithm, most of the machine learning algorithm, what we did is that it is some statistical model. The statistical model we see here is actually a model that encounters some randomness, not only from the data we collected, also from the model. Okay, it's depending on the initial seed. It depending on how we use data as the training data. It's also depending on what data are selected into the training data. So we use the random split here to split all these data into the training data and the test data here, because we think the random state here can make the data random enough for the training. Okay, it is just a very simple problem. And we set the test sets with 0.2, which means 20% of the data set used as the test set. And the rest, 80% is used as the training set. Some students ask whether there are some specific percentage used here. Okay. The selection of the size for the training data set and also the test data set, depending on the problem you encountered and also depending on the data set you collected. If we have a very large data set that can contain almost all the cases we encounter, okay, we can set the test set to be the relatively smaller value. 0.1 is also acceptable. And some other cases that the data set is very, very small, very, very small. For example, like I just showed here, we have only 34 spectral class with 4. If we set a data set like okay, 80% as the training data and 20% as the validation or as the test data, if we calculate the spectral spectrum class 4, it's actually around 20 20 targets or 20 galaxies are included in the data set. If the spectral class is very important in the redshift estimation, it will make your model very unrobust in the application. So in the actually in the real application of the machine learning algorithm, sometimes we use the key for test here, which means you select some data here, test at 0.1 or 0.2, and you train the model multiple times. And each time you get a model and you evaluate the model performance, and you evaluate the model performance for 10 or 20, sorry, for 9 or 8 times and evaluate the performance in 2 or 1 times to see whether your model actually converges to a to a state that you are very satisfactory to it. Okay, it is how we split the data into the training data and the test data. Okay, we just run code here. We just split the data. The training data size is actually 10,624, and the test data is 2,054. Like what I said here, in this step, you can actually did a lot of times, split the data set, train the model, and validate the model performance. Do not to be satisfactory to a performance that you said your model is 90% or 98% accuracy. It is just some illusion. If you did some different data splitting here, you will get different results. So validation, the model performance should be very careful, especially when you want to use it in some real applications. Okay. After we define the data set here, and next step is that we define how I think the model is good or bad. Okay, for the regression evaluation, we use something like actually some four. Let me see four. Okay, some four different evaluation method. Actually, you can also define it by yourself. Okay, these four is some very in some algorithm, sorry, in some functions that we frequently used in our application. The first one, the mean absolute value, which is MAE, which calculates the absolute difference between the yi and the y hat I, which means the value predicted by your model and also the true value. Okay, it is some absolute difference. For the second method, for second different evaluation function is that the mean square error, which calculated as MSE, calculates actually the difference between the predicted value and the true value and the square values of them, and we calculated the mean value of this. Okay, we will discuss difference between the four functions after we show all these things. The root mean square error is actually the squared of the MSE, okay, like MSE, and the R squared square, which is a coefficient of determination, actually calculates the model, the variance of the model or variance of the model. Okay. And as I said earlier, that if we just think about the difference between the predicted values and the true values, we can see that all the first three models, functions can reflect the performance of the model. But when we choose the MAE, when we choose MSE, and there are some we see the N model, which means we can replace number 2 here to N to N, to M, okay, which is M squared of these values. Okay, if we check carefully about this model, we know that there are still some different sensitivities for this different function, because for the small difference here, we can say that the MAE for small difference, which is smaller than 1, the MAE is actually is larger than MSE. But if we see some larger difference, for example, the yi minus y hat I is larger than 1, the MAE should be should be smaller than the MSE. Okay, if we replace 2 here to some very large values like M, 3 or 4, we can see it increase dramatically when we have large difference, but it will drop dramatically if it is smaller than 1. Okay, it's the difference between these different functions. So for your applications, it depending on your estimation of the performance of your model. If we say we are very careful about our model, okay, we say we want our model to converge to the different converge to the predicted line. We can use MAE, and if we are so we are very interested in. Okay, some people ask some question. I will just hear. Okay, some how did you open okay, you can just open the split pie. I will answer these 2 questions here. The first is how we can open some functions. For example, okay, I just show up to. If you want to say some function, you just put your mouse here and oh, sorry, split tree. Okay, and then there are some function. The description of the functions will come out. It's just a README file. Sorry, we README part in the Python file. And if you want to see the source code, there are something to see the source code. Then you can see the source code. Okay, you can actually see the source code for every function in some Python library, so you can know what is the basic idea about these things. The second question is if we predict the value, does it mean we do? Yes, we do not know the true value for okay, let's switch to a different answer method. Okay, actually the machine learning algorithm is what we say like prediction. Okay, prediction. What does prediction mean? Prediction means we have some collected of data. We know the answer of this data, and we want to use our model to learn the relation between the answer of the answer and the feature. Okay, then we will use the model which is trained by what I just said, the data we collected, and we plan to use the model to do some calculations that we do not know. Okay, do not know. For example, show us. Okay, let's one by one. First, about how uh, okay, it's like when you prepare for the examination, you do not know what the examination that will come, what are the problems will in your in your future examination, but you know that there are some questions that are related to the examinations, so you will practice yourself by solve these problems laid by your teacher. So it is what we did in the machine learning. Actually, the supervised learning, we have some examination. We say not easy. We have some tests here. We know the answer, and we train the model, and the model will solve the problem in the future examination. Okay. The second question is some other methods. Okay, some other methods like what I said earlier. You can use different squared here, like 3 or 4. Okay, they represent different we see the regression error calculation method. Okay, let's continue. You can check these things. There are a lot of materials or papers discussed about how to define different evaluation function for the regression algorithm. Okay, let's continue. Oh. Okay, let's continue. After we define, okay, there's R squared we do not discuss here. R squared we see here, the definition is very interesting. The something here we use the average values of y, and some here we use the yi squared, sorry, yi height, which means that the deviation of your model from the prediction value. It's actually I said earlier, calculate the variance of your model okay, variance of your model. If it is -2, if it equals to 1, it's perfect direction. If it is uh, equals to 0, the model does no better than me. And if it is minus, okay, there are some wrong here. Okay, I squared. Okay, if smaller than 0, model is worse than the predicted mean. Actually, it is like if you want to do some guess, okay, you guess a number like a 1 or 0. Okay, the random guess 1 or 0, if you compare it to the ground truth value, it is actually 50% that you will get the correct result. But if I squared is -0 means that it is worse than the random guess. Okay, more information you actually can check here with the regression matrix. Okay, after we define the matrix here, we actually use some function, define the functions. Although these functions can be directly directly called by the scalar function here, we use the mean square error, R2 squared, and mean absolute error. You can also define it by yourself because actually it is some simple mathematical calculation here. Okay, and now we do the calculations here, and we just check the performance of the model. Okay, you press the shift control, sort of the shift enter, you can get the this function definition. And after you define this function, you can actually do the regression. Okay, as I said earlier, the linear regression, the last regression, which use L1 as the evaluation function. Okay, L1, what is L1? L1 means uh, you define it as 1, it is L1. And L2 here means if you define it as 2, it's actually MSE. Okay, it is L2 regression, or also called ridge regression. And there are some other machine learning algorithm that we do not discuss in this lesson, like the key nearest, which is calculate the key nearest lab, sorry, which is used to which is calculates the nearest neighbors, the labels of the nearest neighbors to define what this what it belongs to. Okay, the decision tree actually you build some decision tree with some with some features, and you calculate the importance of the features, and then you build a decision tree to actually get the result. The maximum depth means how the depth of the decision tree is. And the random forest is actually you build several decision tree to to build several decision trees and made this decision tree like a forest. It's called a random forest. We just remember these things, and all the algorithms should be discussed in the next lesson, in the next week. We use it here to just show the difference between different, we say, the regression evaluation factor. And the last one is support vector regression. Okay, it is actually you build some SVM machine, or not machine, or SVR to classify these different types. Okay, we just ignore the 4, 5, 6, and 7 different algorithms which we'll discuss in the next lesson. And we just show this estimation and to see the result here. If you press shift and enter, you can get the results like if you use line regression, and it is the predicted redshift in the y-axis, and the true redshift here is in the x-axis. And we know that if we build a model that is good or that is acceptable, all the pixels should be lying in this red line. Okay. However, actually, if you see this distribution of different pixels, you can see a lot of pixels particularly for the not height, for the redshift that is larger, it will distribute in some different regions. Okay, so if you check the MAE and RMSE, you can find the values actually is something larger. And if you check the R squared square score, you can find that is 0.45. And you return back to the definition of the I squared. If it is 0 to 1, it's perfect direction. If it is between 0 and 1, it actually means it's good, but not good enough. Okay, it's not good enough. Okay, and if within the residual of the redshift estimation, okay, the residual, you can see that it is no, it actually looks like a normal distribution between minus 0.05 to 0.45. However, there are uh, a lot of uh, galaxies that estimate the redshift in this region, and we can find that there are all these galaxies. Okay, let's continue to Lazo regression, which is use L1 as a regression method. Okay, we can see that the MAE between these different methods actually differ little, and R squared actually is also similar. And if we check the distribution of this arrow or the blue dots, we can see that they also have some normal distribution. Okay, in the high redshift, or see the redshift value is larger, it will just in this region. And okay, and we find that the distribution of these prediction results also for the large redshift region here, and actually the pixel distributes here. Okay, for the L2 method, and we can also get some similar results. Okay, just some similar results. And for the key NN, we see that it gives some better result here. Okay, if you see that MAE RMSE is smaller than previous method, for the R squared value, it's very close to 1. Okay, very close to 1. We can check, also we can guess. It looks like it get some good result. Okay, for the distribution error, we can find that it distributes to the center, to 0. Okay, to 0 of the results. It's for key inverse neighbors. And for the decision tree, we can get some similar results, but it's not as good as key nearest neighbors. Okay, it's the distribution of the blue dots. Okay, actually, a lot of blue dots in this region, which is not quoted in our previous test, and also the dots in the high redshift. Okay, in this region, they becomes closer to the red line. Okay, the result here looks like they distributed in the center, and we just move on to random forest regressor. Actually, it similar to random tree, sorry, to the tree decision tree. And the last one is SVR. Okay, it looks like uh, it is not better than the random forest, but similar to some other method. Oh, sorry, it's better than the L1 or L2 regression, but not as good as the random forest. Okay, 80th step, we just check the performance of the regression algorithm with the data. Okay, before we move on to do some data sorry, not data augmentation, actually the data regression, sorry, the data scaling. Because we do that, we can just from these results to see which model is better, and when we do something in real applications, which model we should use. Okay, all the machine learning algorithm you encountered in your future no, uh, is future study or future scientific research. It follows the same rule. You pick some model, you select the parameters of the model, you select the evaluation factor of the model, you just run the model in some data, you check the results with the test data and to see which model is better. From all these tests, we can say that if we want to choose model, we may choose random forest, or we may choose a decision tree. Okay, choose a decision tree. Okay, so it is a step here, why and how we choose different machine learning algorithm. Okay, and before we move on, we see that the line regression model performs poorly compared to KNSVR of the SVM distributed rainforest. Okay, why it is worse than this model? Some people say that if we use a very complex model like random forest decision tree, it is obvious it should be better than some simple model like random regression. It is one reason. Another reason is that we do not treat the feature correctly in our in the application. Okay, so we see the feature scaling is very important. The feature scaling, if we choose some very common problems in our real life, like if you check some people's face, okay, if you check his picture, you say, okay, this is some people I know, and if you see other pictures, that it is some people we do not know, and how people check picture of different people. Actually, we use something like important feature. For example, if you see people, you will just check the eye, the nose, the mouth, and the ear, and the hair of the people. Also, some the shape of his face. Okay, so it's the feature scaling. Some features are important, and some features are not important. And in real applications, we need to choose important features, and we also need to scale these features into the same scale. For example, if I want to evaluate the weight of people, and we can use different method. Sorry, different unit. For example, we can use a kilogram. We can use gram. Okay, and if you use gram to represent the weight of the people and also the height, if you use a meter, okay, you will find that the if you use meter to evaluate people's weight, it will be around 1 or 2. But if you use gram to evaluate the people's weight, it will be around like uh, okay, like several hundred or 100. Sorry, several. Several thousand. Uh, several thousand. Sorry, not several. 100,000 gram. Okay, you will find that the difference of value is very large. So if you design some machine learning algorithm to use all of this data into your machine learning machine learning algorithm, you will find that the height of the people will become not very important because the difference of height in meter will be very small, but the difference of people's weight in gram would be very large. So it is why we do the feature scaling. Okay, feature scaling. So just some 3 points we need to remember that models may become best toward features with larger magnitudes. Optimization algorithm will take longer to converge just because of the feature scaling is different. And models rely on distance, like KNN or SVM, which calculate the difference, the distance between the sample points or the anchor points and also the points you want to classify may produce suboptimal results. It is why we need to do feature scaling. Okay, and how we do feature scaling? We do feature scaling just to put all these features within the same scale. It is just the basic description of the feature scaling. Many different methods can do feature scaling, like minimax scaling, which you can scale all the values x max minus x b and x minus xb to divide x max minus xb. You can get a scaled x which distributes around 0 to 1, and it's called mini max scaling. Okay, it is a normalization. Sometimes called sorry. Sometimes it's called the minimization. Let me just close this. Sorry. Let me close the source code. Okay. It is called the normalization. And also in neural network training, we have something like a batch normalization or instance normalization. It's just do this, okay? The second thing is like standardization. Standardization, we also call Z-scale normalization. It's did a little different thing with the minimax scaling because in the standardization, we do not only put all the values to 0 to 1, we want to the variance of the data to 1. So we want the data to distributed a normal distribution. So we use x minus mu, which is the mean values of the feature, to divide the standard deviation of the feature. Okay. With the z-score normalization, all these scaled values will distributed have some Gauss-like distributions. Okay, Gauss-like distributions. So if you set all the features to Gauss-like, actually the algorithm will that follow the Gaussian distribution will have better performance, like logistic regression, line regression, sport vector machine, and PCA principal covenant analysis. Okay, it is called z-score normalization. And there are some other methods like robust scaling, which use the IQR, which quantile range of the data as below here, and also use x minus b. When we use the robust scaling, actually we know that we can rule out some data that's distributed out of the range. For example, if I want to evaluate the height of people, I want to scale out Yao Ming from our data set because he's too tall. So we use a robust scaling. The max app scaling here use the maximum value is there in here, and we use x divide max x absolute value here, and we use it to rearrange our data into the distribution, and we can preserve sparsity in sparse data set. Okay, it's normally used for text data. Okay, it is some different scale method, and I have also discussed why and how we use a scaling method. And after we use scaling method, the next step is we scale all these features here. And after we scale these features, we can see that the scaled feature distribute around zero, and it is all these features like u minus gg minus r minus I minus z, the values are distributed here. So with these features, we can say we just retrieve the model to see what will happen here, and we use the model to treat the we use the scaled values to treat the different model like line regression, range, lasso, KNN, decision tree, random forest, and VR. We can find the results here. Okay, let's just wait. The code is still running in the background. Okay, for the line regression, we can see that oh, okay, it's just wrong. Finished. Okay. Okay, after we rescale the data, we can say that for the line regression, the B-square error is small, but also the key decision tree and random forest should be smaller. And we can see that the random forest becomes the best classification. Okay, not class, actually it should be regression. Random forest regressor would be the best algorithm used discussed in all these part. Okay. I think that is the step and how we use a machine learning algorithm to solve the problem. Okay, before we move on, I just do want to make a conclusion here. When we do the machine learning or when we pick up a machine learning algorithm in our real application, what we need to do is just check the data to see whether all this data or the noise in the data we have actually removed. It is the first step. We see the pre-processing of the data. The second step is actually we need to do some feature selection, or we need to pick up important features. Like we did here, we use the difference between different magnitude to carry out our the redshift estimation. Every people can just check if we directly use the FRGRI for the test, what the result will be. And the third step is we need to actually select the model. Before we select the model, we need to use our physical intention to check to think about the problem we want to solve and to think about the data we have collected. And we need to split all the data we have here to training data and test or validation data, and we should select the effective, or we should uh, select the good evaluation. Because we do regression here, we use regression evaluation. If we do classification, we need to select the classification evaluation factor here, and then we can pick up a lot of different algorithm here to use the adequate data, to use adequate regression or evaluation factor here to check which model is the best. And if we find that there are some weird things happen, we need to think about whether we did the correct feature scaling, or whether we need to rule out some data that's not that will make our model worse in the real application. Okay, I think that is all the part I want to discuss here in this hour. Okay, and are there some questions you can directly ask me? And let me check uh, PRD as well. PRD, RPD. Can you can you just tell me what the RPD is? Okay. Your email ID. Okay, I just show me my email is okay. It is my email. Okay.
Sorry, can you hear me?
Yeah, good.
That's my
Okay.
question. As RPD is already the ratio of standard deviation to the prediction error, I think.
Regression. Sorry, the RPD means
The ratio standard deviation to the prediction error of the model.
okay. I think we can use it as the calibration for the model. And actually, as I just showed here, the okay. Let's shift back. As I just showed different actually the evaluation factor here. Actually, in real machine learning algorithm, normally we can actually use different. Oh, sorry, we can plus different error together to guide the model to learn some important things because uh, we do not dive deep into different algorithms in this hour. And if we just have some roadmap, when we choose the machine learning algorithm, actually we just choose some surfaces or manifold, and we want to pick out the adequate point that we want to get. Okay, so you mentioned RPD actually can be used to guide the model. You can either we use it as some evaluation function in the sorry, you can add it to the evaluation function. Or also there are some other methods that you can first train a model with MAE as a evaluation function, and before it converges to some stable result, then you can input RPD as some evaluation mode function, and then you can do it.
Okay, thank
Okay.
you so much.
Yeah, good. There are some more questions. Okay. Okay. I will join this class in the next week so we can discuss more things in the next week. Okay. Uh, is it okay? Okay. Uh, let's shift. If we have some questions, we can discuss here. Okay. Okay. Thank you, everyone. Okay. Have a good day.
Thank you. Bye bye.
Okay. Bye bye. Okay. Some people ask the
I'll be
errors.
sharing, yeah, I'll be sharing one more notebook where people can download how they can download Gaia data and do some ML work. I'll just share
Okay.
it with you. So I'll just share it soon. Okay, bye.
Okay, there are some questions I want to reply here. Some people ask, is error the only method to decide which method is best? Okay, it's not only the error, it's also the distribution of the error, which we may discuss the base neural network in our next lesson, because we know that the machine learning algorithm is used to mimic people. So when people do some we say classification or regression, actually what he did is the base estimation. So the error is important. The distribution of the error is also important. So the error is not the only we do not say method, it's only evaluation factor to decide which method is best. Okay. I don't know if I replied the questions correctly. So if you have further questions, you can directly ask me through the email. Okay. Thank you, everyone. And thank you, Professor.
Thank you. Thanks a lot.